Dr. Briony Mamo. She's I'll have to read this because it's the part about the, let's see, she is a Japanese Society for the Promotion of Science postdoctoral fellow in the Institute of Biogeosciences at the Japan Agency for Marine Earth Science and Technology, also known as JAMSTEC. So you see why I had to do that.
So it's quite a mouthful, yeah. Even I have trouble.
She got her PhD from, and I always say this wrong,
Macquarie.
Macquarie University in Sydney. And where she worked on applications of Holocene forams on biodiversity and biotopes from the southern Great Barrier Reef. Probably if you can get it. And she is a scuba diver, and she also worked on extreme events, identification of extreme events there in the Southwest Pacific. And she is definitely a foram aficionado as well as a reef aficionado. She did her honors, which is sort of like a master's, a short master's.
Like, yeah, it's like and you have 1 year, or really more like 8 months to get a research project done, but you don't have any coursework associated with the degree.
She worked on taxonomy, distribution, and taphonomy of deep-sea benthic forams from the New Caledonia Basin, which is partly, I think, what got her the postdoc into working more on New Caledonia.
Yes, kind of, yeah.
That plus the fact that she spoke Japanese, which helped a lot too.
It's handy.
And she did that work on the Marion Dufresne, which is a French research vessel, which says, she speaks both French and Japanese,
only a little bit.
Sort of French. Studied high school. She studied French in high school, you said, and Japanese in college.
Yep.
And so she's served as a lecturer and tutor for a variety of biology and geology courses, and has also been active in outreach in a variety of contexts. And the most important thing is that we're going to get together. The students are doing a TGIF on Thursday, so at the TGIT?
Yeah, TGIT, yeah.
They're
works.
Doing anyway, we can gather at the student lounge afterwards. And then tomorrow evening, there'll be food and beverage at my house, and if you need a map, I've got some maps, or I can send you a map, or most people have GPS these days, and I think I put the address on the email, but if I didn't, you can shoot me an email. And so she's going to talk to us today about sea level fluctuations and paleoclimates from the New Caledonia Basin and identifying extreme events from the Southwest Pacific. And she's promised if she has a little extra time that she's going to tell us a bit more about her work on the Great Barrier Reef as well. So
yeah, all right, okay. Good afternoon, everyone. Thank you very much for coming. I was telling Pam I'm not used to talking to so many people because forum sessions at conferences tend to be a little smaller, but this is great, and I think the fact that you can drink beer whilst doing this is the best thing ever, so cheers.
Remember, she's Nazi, so.
Yeah. As Pam mentioned, what I'm mainly interested in are, Foraminifera, particularly benthic Foraminifera, and the different ways that I can use benthic Foraminifera, like actually taxonomically identifying them, and what sort of applications I can use them in a wide variety of situations. So hopefully this is working. Yeah, so a quick run through of what I'm going to go through this afternoon is, just in case some of you aren't completely sure what a foram is, I will very quickly go through the basics. I promise I won't take too long because I know there definitely are foram workers in here. I'll talk about the paleo environmental reconstruction and sea level rise and fall work I did on New Caledonia Basin, which I presented just at NAPC earlier this week. And then I'll talk about some of the work I did involving natural hazards, so looking at tsunami and extreme storm or cyclone deposits using Foraminifera, whether they're of use or they're not much use, that sort of thing. And then I was directly involved with 2 studies that I'll discuss briefly, and then I think I probably will have time to quickly cover some of the work I did on the Great Barrier Reef and isolating foram biotopes and that existed on the reef as a baseline study, and what environmental factors determined the foraminiferal assemblage in that region. Okay, cool. So forams constitute a very important part of the marine food chain, and they contribute 1.28 billion tonnes of calcium carbonate per year, which is approximately 25% of the yearly global ocean carbonate production. So even if they're not important as a fundamental component of the benthic ecosystem, they're pretty important with carbonate production as well. So they're single-celled heterotrophic organisms, they're eukaryotic, they're characterized by a mineralized shell, which we call a test, and granular pseudopodia, which are these little extensions coming out of the test. Fossil forams have been found up to sizes of 19 centimetres. However, modern-day forams tend to be around 100 microns, generally up to 2 centimetres. However, there is one species of foram around southern Japan that I only discovered last year. Well, other people knew about it. I didn't know about it. Called Cyclopia, I think. And Cyclopias. And I saw one, and they grow up to about 7 centimetres in diameter. They're absolutely huge, and they're really cool, and they live fairly deep off the reef edge. There's about 10,000 living species of forams. However, genetic studies think that there are probably quite a few more. So this, just to give you an idea of what their pseudopodia look like. So the pseudopodia are used in feeding and locomotion and lots of other things. This is just a really common species of foram that my boss works with at Jamstack, Paleo opercularis. And this is it working? Yes, it's working. So basically I just got this guy and put him in a petri dish, and he's extending his pseudopodia, and then he's using them to pull himself around the petri dish. And I don't know why it's a he, it's not a he, it's just an it. Anyway. So this is what the foram looks like, and the pseudopodia are all extending outside of these apertures on the base of the test. And so it is going to pull himself. It's going to go back to where it was. And then if you want a close-up of those pseudopodia, this is what they look like. Depending on the species, they can sometimes just be extended, but with Planoglabratella opercularis, even if the foram is stationary, the pseudopodia are still constantly in motion. Right. So they inhabit the entire marine realm at all latitudes and depths. More importantly, individual species of Foraminifera are extremely sensitive to certain sets of environmental conditions. The majority of Foraminifera are benthic, living on or in the sediment, in the upper few sort of 5 to 10 centimetres of sediment, mainly the top 5 centimetres. There's a small number of planktic taxa, about 60 species, and they float at various depths in the water column. So you can get 6 types of tests. However, fusulinids are extinct. Proteinaceous and siliceous are not very common, and they're benthic. I will mainly just go over agglutinated, porcelainous, and hyaline test types because they're the most common, and they're the 3 types that I work with the most. So agglutinated foraminifera have a basal organic layer, and then they use either an iron-based or a calcareous-based cement to pick up pieces of crud around them and stick them to their test wall. They are sometimes selective. So you can see this biserial type here only wanted pieces of silica to stick to itself, or they're not really fussy and they'll just stick whatever is surrounding them. Porcelainous types have a basal organic layer, and then they have an ordered inner and outer layer of calcite, and then they have randomly oriented rods of calcite throughout the middle of the test, and it gives it a porcelainous appearance, which, porcelain appearance, which means that it's kind of easy to remember that they're called porcelainous. And then finally, hyaline tests have the basal organic layer, and then those calcite crystals are radiating outward, and they're all in a parallel direction. And so because they're all in the same direction, it gives it a glassy or a perforate appearance, like these 2 examples here. So there is a wide variety in the types of tests that you can get with foraminifera. You can have like a gorge shape, you can have a uniserial, where all the chambers are stacked on top of each other, or they're biserial, triserial, they look like sausages, they look like wheels, they look like spirals. And in one locality, this is a reef assemblage, you can get quite a range. You don't find necessarily the exact same morphotypes inhabiting the exact same environment. And they also have a big range in apertures. So apertures are through which the pseudopodia extend. You can have a single hole, you can have like a silver plate, or you can have these anastomizing sort of openings, or you can have sort of mushed up looking holes. There's lots of different types. So, why are foraminifera of so much use? As I mentioned earlier, there it is. So the environmental sensitivity and the distinct morphology of various species. So basically, because they're so morphologically distinct from each other, if you know what you're looking for, they're easy to, you can identify them, and then you can associate specific species with specific environmental conditions. And so they're exemplary tools for a lot of paleo and modern applications. So you can use them for things like monitoring the health of an environment. If there's an environmental change, like if oxygen conditions change in the water, it will be reflected in the foraminifera living in that ecosystem. As you're going to find out today, they're used in paleo environmental reconstructions. You can see how an assemblage changes through time, so therefore how the environment changed through time. We already know, well, they're commonly used in dating. They're used in oil via stratigraphy, and you can also use the discoloration of a foram test to tell you how much heating the area has undergone, so whether there's oil associated with that level of heating. And then you can also, they've used them in stone provenance in archaeology as well. They've looked at the forams in the sandstone, and then they've found where the quarry... It's okay, little guy. They've found what quarry they got the stones from, so they're kind of cool. Right, so moving right along to the first application of forams. This is, as Pam mentioned, this is my honours work, so it was a very short 8-month-long study. I did my training on the Marion Dufresne, and what basically happened was we're just here in New Caledonia. I didn't collect the core myself, but I did work in this region along the Norfolk Ridge. This is Australia here, Lord Howe Rise, and I worked on a core that was just collected here off the northern Norfolk Ridge and off the southwest coast of New Caledonia, where it's quite deep. It's just on the shelf. Okay, so basically way back in 2001, before I was doing my honours, the RV Franklin retrieved the core. What the whole point of the RV Franklin cruise was to sample the seafloor, the water column, and the water surface, to use a whole range of different proxies to understand what had happened in the New Caledonia Basin over the past 150,000 years. What I did with GC4 was basically looked at the foraminifera, picked them out, counted them, identified them first, then counted them, and then looked at what environmental associations I could get from those species, and so look at how the environment had changed, at least at that location, at the sediment water interface from about marine isotope stage 6 through 1, because they figured out with GC4, the girl that worked on the core before me had figured out that the top 141 centimetres of the core equal to about 140,000 years. So as I mentioned, my colleague Elsie Gretton used the planktic foram, Globigerinoides ruber, to do oxygen and carbon isotope analyses, and she figured out that 1.46 centimetres equaled about 1,000 years. And then she also figured out a range of oceanic conditions, salinity, productivity levels throughout that period of time. And so she discovered that the Southwest Pacific Ocean, that area, was characterised by higher levels of evaporation and lower levels of precipitation than the rest of the Pacific Ocean for that extent of time. Sea level minima periods during interglacial stages, MIS 3 and 5, were characterised by high winds, increased surface salinity and lower temperatures. Glacial period 4 was a warmer glacial period than other periods of sea level low, and significantly more arid conditions prevailed throughout the transgression between marine isotope stages 2 and 1. So this is just a graph of her work. You've got the oxygen and carbon isotopes. This is the sedimentation. You've got time down the left here, and these are the marine isotope stages. So you can see there's a bit of change, particularly in sedimentation and oxygen. Ooh, excuse me, it's beer burping. All right, so what I did was I picked the foraminifera every 2 centimetres in the uppermost 30 centimetres of the core, and then I took 2 samples every 10 centimetres for the remainder of the 141 centimetres of section. I identified the taxa, counted them, looked at epifaunal versus infaunal species. So epifaunal are species that live on the sediment, or they might live attached to something that's sitting on the sediment. And then infaunal are those foraminifera that live in those uppermost centimetres of sediment. I used Bray-Curtis Q-mode cluster and multidimensional scaling to isolate the assemblages in my section. And then I also looked at Fisher alpha and Shannon-Wiener to look at species richness, so diversity, and look at species evenness. So is there a dominant species that was sort of taking up most of the assemblage, or did you have a relatively even spread of abundance? Okay, so I identified 161 species. However, only 46 of those species were abundant enough throughout the core that I could use them in paleoenvironmental interpretations. The most abundant was Epistomonella exigua, and it had an inverse relationship to species richness. So if I had a large percentage of Epistomonella exigua in that assemblage, then I had low species diversity, and vice versa. There were several other key abundant taxa that I could use that were really strong indicators of certain environmental settings, and I also had a couple of species that were indicators of deep oceanic currents that were operating in that area. So Epistomonella exigua is an indicator of Pacific bottom waters and the Antarctic bottom waters, and Orodorsalis umbenatus is an indicator of the Antarctic bottom waters. So it was pretty rare to find any specimens that weren't somehow damaged. So the most common types of damage were fragmentation or abrasion from being transported around. There was a fair bit of corrosion. There was drilling predation and a lot of encrustation by manganese and pyrite. And you can see little perfect squares of pyrite just on this uniserial foram. Okay, so if you look at the distribution of the key or the most abundant foraminiferal taxa, and this is just everything else, through the section of core, this big section is Epistomonella exigua. This big section up here is Bolivina compacta, which I'll talk about a little bit later. Other key taxa include Euvigurina hispida. And anyway, the point of the matter is that you can see around this section, there's a change quite a drastic change that's occurred at the core around this 20 to 21 centimetre horizon. And then if you look at the epifaunal versus infaunal abundance throughout the section of core, you can see that again at that same horizon, there's a change from an assemblage that's pretty much dominated by epifaunal taxa to one that's dominated by infaunal taxa. So obviously there's a drastic change that's occurring at the sediment-water interface. So if you plug all the data into Bray-Curtis and MDS, you've got 2 really nice clean clusters popping out. You've got foram assemblage 1 that starts at the bottom of the core and goes up to that 20 to 21 centimetre horizon. And then you have foram assemblage 2, which is those uppermost 17 centimetres. And then they pop out again quite easily with MDS. So this is just another way of showing the same data. You've got the marine isotope stages, and these are the dominant taxa that are associated with those 2 assemblages. This is foram assemblage 1. You can see they're pretty happy down here, and then you've got some dropping out in this uppermost 17 centimetres. And then here are those foram assemblage 2 taxa where they're having a real big peak around that 20 to 17 centimetre mark. And this is a sea level curve, so you can see there was a pretty drastic sea level rise at that point in time. So if we were to run through both Elsie Gretton's work and mine to pull together a scene, a sort of setting the scene for foram assemblage 1. So it existed, it's from the base of the core to 20 to 21 centimetres. It's dominated by Epistomonella exigua, which is an epifaunal species that's known to respond to pulsed increases of organic matter. There are large numbers of lower bathyal to abyssal species, so they're typical species that inhabit those sorts of environments. The Fisher alpha range from 10 to 29. So it's typical for a bathyal marine setting to have that sort of richness. Shannon Weiner range from 2 to 3.5, so it's only a low to moderate species evenness. Basically, this is an assemblage of well-oxygenated waters of deep sea depths with deep water circulations. And so this assemblage is influenced by levels of oxygen at the sediment-water interface, nutrient supply, and the sort of varying conditions you have between interglacial and glacial periods. All right, forum assemblage 2 is in the uppermost 17 centimetres, however it wanes towards the present. Bolovina compacta was the most dominant species. It was characterised by other infaunal species that are typical for low oxygen conditions. There was an average of 55 species per sample. There was only an average of 35 in forum assemblage 1. You've got higher Fisher alpha values, so it's a rich assemblage, and you've got also higher Shannon Weiner values, so there was a more even spread of species abundance. You didn't have that stark dominance by Epistomella exigua. It's typical of an upper bathyal to shelf marine setting, particularly Bolovina, Bulimina, and Eugerina are key indicators of low oxygen conditions. And then so this assemblage has basically had relatively high sedimentation rates related to high sea surface productivity and associated eutrophic conditions. Now, there were several other instances throughout GC4 where dominant taxa, or normally quite abundant taxa, had their abundance lowered, or they dropped out of that horizon completely, and I wasn't really sure why, because it was irrelevant of whether it was forum assemblage 1 or 2. But what did happen in those horizons was you had an increase in the abundance of these Euvigderina species, particularly Euvigderina hispida. So basically, Euvigderina hispida is an infaunal species that is quite happy in eutrophic conditions. So both Euvigderina hispida and Epistomella exigua both respond to pulses in detritic matter being delivered to the sediment floor. However, whilst E. exigua can only sort of tolerate lower oxygen conditions, Euvigderina hispida thrives in them. There was also a couple of instances, so these two species, Cibicidoides wellestorfi and Cibicidoides dispars, they're an epibenthic or an epifaunal species, and their abundance they mimicked each other throughout the call, regardless of whether it was forum assemblage 1 or 2, which was interesting because in the literature it says that these species